here we are going to understand the concept of moving iron instrument. We have got a problem here, but before going to the problem, first we look at some basic concept of moving iron instrument. Now, what is the purpose of using moving iron instrument? As we have discussed in our PMMC instrument, the purpose remains the same, as it is used as some types of meters like ammeters, voltmeters. This kind of meters are made using the moving iron instrument. Another purpose is it can be used both AC and DC measurement. Now this is a schematic diagram of attraction type moving iron instrument. So it is mainly of two types. One is attraction type, another is repulsion type. Okay, repulsion type again maybe two type: radial vane type and coaxial vane type. But for understanding this given problem, attraction type moving iron instrument conception is enough, as there is not much difference in this different type of moving iron instrument, that is attraction and repulsion. The only difference is this is a soft iron piece. When it is attracted towards the coil, it is called attraction type, and when it is deflected by creating the same pole, then it is called repulsion type. The purpose is same, to use it as various type of meters, only the working principle is different. Now let us discuss about the mechanism of attraction type instrument. See, what is our objective? Our objective is to measure the value of electrical quantities. For that, what we really need to do? We have to rotate the pointer, this pointer. How could we rotate that? If we can generate a torque. Now how are we generating the torque? When we are sending current to the coil, which coil? This coil, this coil. Then the coil is generating a magnetic field. When the coil is generating a magnetic field, this soft iron piece gets attracted towards the coil. So let us name it the point 1, this is 2, this is 3, 5. So when the soft iron piece gets attracted towards the coil, then the pointer is attached with the soft iron piece, so it is also deflecting. So when the pointer is deflecting, it is showing a reading on the scale. So the thing is, I think, very clear to you. So let us recap. First, our objective is to measure the electrical quantity, whether it is voltage or current. For that, we need to rotate the pointer. So how could we rotate the pointer? If we could generate a torque, so we need to generate a torque now. How could we generate the torque? If we can generate a magnetic field. How? By flowing a current through the coil. Now whenever the magnetic field is generated, then this soft iron piece is attracted towards the coil. So when the soft iron piece is attracted towards the coil, this pointer is attached to the soft iron piece, also get attracted or deflected. Whenever this pointer is deflected, automatically we are getting the reading on the scale, because this particular iron piece is free to move. So the mechanism, I think, clear to you. Now from this mechanism we have come to know that there is a generation of torque, and that is a deflecting torque. So In moving iron instrument, the expression of deflecting torque, that is tau d, is equal to half I square dl d theta. Now what is I here? In the question, see, the value of current that is passing through the coil or the instrument is I. Now what is L here? L is the value of the inductance of this coil. And what is theta? If it is a zero position of the scale, when the current is flowing through the coil, then the pointer is deflected from the zero position. Let us assume that the zero position is here, like this. So after the deflection, the pointer is shifted to this particular position. So what is the angle of deflection? This is the angle of deflection. This is theta. This is given in the question, theta. Okay, theta is the total angle of deflection from initial zero position to its final position of the pointer. So all this thing is clear now. Another thing is, when the flow of current through the coil is zero, that means there will be no current flow through the coil, then this particular pointer has to come back its initial zero position, because the flow of current is zero. So pointer should read at the scale zero value. Now who is responsible to getting it back to its initial position? It is called controlling torque, or tau c, and is expressed in the form of k theta. K is the controlling torque constant and theta is the angle of deflection, because as I have said, the angle which is deflected due to the deflecting torque has to be fulfilled or covered up to bring back the pointer to its initial zero position. So from here we are seeing that deflection, or the amount of deflection, is equal to the amount of control. That means deflecting torque is equal to controlling torque. So from the previous expression we can write half I square dl d theta is equal to k theta. So from there we can write theta is equal to 1 by k into half I square dl d theta. This formula is very important in terms of our problem solving purpose. Now let us solve the problem. The inductance of a moving iron ammeter with full scale deflection of 90 degree at 1.5 ampere. Okay, so whenever you are flowing a current of 1.5 ampere to this coil, this pointer goes to at its final position. This is the full scale deflection, or FSD. Okay, and the expression of L is like this in microhenry, and theta is the deflection in radian. So you have to calculate that when the current flowing through this coil is 1 ampere instead of 1.5, how much the pointer will be deflected. That means what will be the value of theta then. So from the equation we have learned now is theta is equal to 1 by k half I square dl d theta. Here see, I is equal to 1.5 ampere, we know it. We can calculate the value of dl d theta. We know the initial deflection of the pointer, that is 90 degree. What we don't know is the value of k. So first determine the value of K from this equation. So K is equal to 1 by theta into half into this expression. So just convert theta in radian, that is 90 degree means pi by 2, and into d theta of, like this. From here we can write like this. Now put the value of theta equal to pi by 2 in this equation. We get simply by calculation 14.32 into 10 to the power minus 6 Newton meter per radian. This is the expression of K. Clear? Now what is our objective now? We have to calculate the value of theta again when the current changes to 1 ampere. So write the equation once again. Theta is equal to 1 by K into half I square dl d theta. Now theta is equal to, we know the value of K now, I equal to 1 now, and dl d theta is equal to this same expression like this. So from here we can straightforward write like this. So from here just calculate and you will find the value of theta is equal to 1.008 radian. Now if you want to convert this radian into degree, just multiply it 180 by pi, that is 57.8 degree. So when 1 ampere current will flow through these coils, then the pointer will be deflected. The deflection will be 57.8 degree. That means this particular angle is 57.8 degree. So why MI type instrument has a non-uniform scale? That means when we have a uniform scale, then the distance between the 2 point or 2 reading will be same. But see, the distance between 5 and 6 a little bit smaller, like 3 and 4. Though this diagram does not depict properly the uniform or non-uniform scale, or better we can call it a uniform scale. When we have a non-uniform scale, then these distances from 1 to 2 will not same like 2 to 3. 2 to 3 distance will be higher than 1 to 2. So the divisions in between this will be increased. That is called non-uniform scale. So if you look at an MI type instrument, there is a non-uniform scale. My question is why? Whether in case of PMMC instrument you will find this type of uniform scale, but in case of MI type not. There is not uniform scale. So mention in the comment section below your answer with logic, and if you have any doubt then you can also mention in the comment section below. Thank you.